Okay, here we are with a quick review of all of the exponent stuff. So first of all, let's go through the rules and review some of the basic ones. So if we have something like x squared times x to the seventh, what does that equal? Well, they're multiplying here, but the exponents are going to add. Now, why is that, you ask? Well, let's go and we have, there are two x's here. That's what x squared means, times itself, and there are seven x's right there. 6, 7. Well, there are 9 x's all there timesing each other. So that's why they add. Well, let's do something like x squared to the 7th. And what is that guy? Well, that's going to be x to the 14th power. And why is that? Well, because you got x squared 7 times. So x squared, 3, 4, 5, 6, 7. And 2 plus 2 plus 2 plus 2 plus 2, according to this up here, is going to give us 14. There we go. That's the next rule. So what if we did x to the 7th over x squared? Well, look at this. If multiplication leads to addition of exponents, then division would lead to subtraction. Now, is that true? Of course it is. 1, 2, 3, 4, 5, 6, 7, all times together up on top, and then there are 2 down below. This one cancels with that one, making 1. That one divides that to 1, cancels, and we're left with, oh look, 5x's left at the top. So this is, you're going to add exponents, you're going to subtract exponents to simplify them, or multiply them here. Well, what happens when you have subtraction? You end up with negative exponents. So if you have something like x squared over x to the 7th, well, according to this rule, that's x to the negative 5. But in slow motion, it's because we had this. Yeah, cancel, cancel. We left a 1 up there, and this is 1 over x to the 5th. And that's exactly what happens with negative exponents, is they flip things over or divide by them. So really it's a subtraction with whoever wins. If 7 won, you got 5 bigger on the bottom. If 7 wins on top, that means it's bigger on top, so you're going to win and remain on top. Ooh, but what happens when you do something crazy like subtraction, like an x to the 0? Well, that means you had a 5 minus a 5, like an x to the 5th over an x to the 5th. 5 minus 5 is 0. Well, anything over itself is the number 1. So let's try a couple of these. If I have 2 squared times 2 to the 7th power, this is actually 4 times 128. Wow, what's that? 512? Yeah, this is 2 to the 9th. Notice this is 2 2's and 7 2's. That's going to be 9 2's all times together. We don't have this be 4 to the 9th. 2 times 2 there. 2 to the 3rd to the 4th. You're going to multiply those. Those is 2 to the 12th. If we have something like 128, which is 2 to the 7th, over 4, which is 2 squared, that is indeed 2 to the 5th, or 32. You should try this for size every once in a while. 2 to the negative 5 power. And yeah, that's going to be 1 over 2 to the 5th. So it's exactly the same as 2 to the 5th, but it is on the bottom. This is 1/32. And then, of course, 2 to the 0, that's going to be a 1. 5 to the 0 is 1. Anything to the 0 is 1. You should check that in a calculator. So the final thing is when we have roots, like x to the 1/2 power. That's the same thing as the square root of x. X to the 1/3 power is the cube root of x. X to the 1/4 power, and so on. And you can see that using this rule right here. If we take the square root of x squared, that's going to give us an x, right? For all positive numbers. Well, that's the same thing as x squared all to the 1/2 power. Multiply these and you get to the first power. So yeah, a fractional exponent is a root. So we could have something like 32 to the 1/5 power. And that's the 5th root of 32, goes backwards on this one, equals 2. So we have here a nice little game we can play. This right here is a little, well, some practice. Let's go through these and make sure we can do some of these with numbers. 6 to the negative 3, so that's going to be 1 over 6 to the 3rd power is 216. So that's 1 over 216. 2 to the negative 4, so we take 2 to the 4th power. That's 16, and that's 1 over 16. Okay, 8 to the negative 2/3 power. So this is 8 to the 1/3 power. So that is right there. 8 to the 1/3 power is 2. Squared is 4 on the bottom. 6 to the negative 2 power is 1 over 36. 16 to the 1/4 power. So there's 16. 1/4 power would be 2. 128 to the 7/5 power. Here's 128 to the 5/7 power, excuse me. So its 7th root is 2. 2 to the 5th power is right up here is 32. 169 to the 0. Oh, anything to the 0 is 1. 243 to the 2/5 power. So here's 243 to the 1/5 power is 3. And then 3 squared is 9. 27 cube root is, there's 27. Cube root is 3. Squared is 9. 625 to the 0 power, that's 1. Do you see how those work? And this little table right here, just like we had the multiplication tables when we were way little small kids, this is something that you really should be able to start to recognize. Certainly the squares are easy. 16 squared is good to know. 13 squared is good to know. 25 squared is good to know. All the cubes, these are the perfect cubes, and you really ought to get to know them. Perfect fourths, that way you can do fourth roots, and it makes it much, much easier. Let's do just a couple more. 81 to the negative 1/4 power, so we're fourth rooting 81, and that's 3. But it's to the first power is 3 on the bottom with that negative exponent. So this would be 1/9. 3 to the negative 4th power is 1 over 81. This is an 81. And 2 to the negative 2 is 1 over 4. 1 over 8. And once you get the hang of this, and this table may be able to help you, you can start doing that in your mind pretty well. Okay, let's take that off and get back to what happens with functions. So now we start dealing with functions. So f of x equals something like 2 to the x. Now, if you look at this with a little xy plot like we've done forever, let's do 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4. We can stick in any number we want up here, even fractions, and we'll be able to get stuff out. So let's stick this in. We get 2 to the 4th is 16, 2 cubed is 8, 2 squared is 4, 2 to the 1st is 2. Notice this pattern, we're dividing by 2 each time, and what happens to be here for 2 to the 0? The right number, 1. 2 to the negative 1 is 1 over that. That's 1/2. 2 to the negative 2 is 1 over 2 squared, 1 over 2 cubed, and 1 over 2 to the 4th. Notice how each of these numbers up here is reciprocated when we stick in their negative. That's kind of a neat little connection. It shows you that this one, will always be there. Anytime you stick in 0, you'll get a 1. That's kind of nice. Couple of things that this helps us to note. Number 1, the domain, we can stick in any number we want. And there's 0, 1, and as we stick in negative numbers, it doesn't go negative, but gets smaller and smaller and smaller. This is going to be a horizontal asymptote at y equals 0. Let's mark that. Horizontal asymptote, y equals 0. And then, let's do, heading up here, it's going to be, those just start shooting up exponentially. Yes, that's where we get exponential. So we'll notice that the domain is going to be all real numbers, and the range, notice, is just everything greater than 0. That's going to be important to note in just a little while. So now we can start moving them around. Well, let's look at the next one. If we have something like f of x equals e to the x, this is a very common number. E is about 2.71828, something like that. It keeps going on for a while. It's like a number pi that happens naturally when things compound on themselves at a constant rate. So e to the x is going to look very similar. So you'll see all the graphs that look like this, and they have the same properties. This one goes up a little bit faster than 2 and will head to 0 a little bit faster as well. A 1.5 to the x would be a little flatter, but they all have the same shape, and this is the cool thing about it, is f of 0 is 1. Will always be right there on that one. So let's try and go to, let's domain and range. Let's move it around a little bit. So f of x equals, say, It could be a 2 to the x or an e to the x, doesn't matter. Let's do 2 to the x plus 4 minus 3, something like that. Now notice what happens here. We take this guy right here, and this plus 4 moves it backwards of what it looks like. So it actually moves it that way 4, and then we're going to go down 3. And let's watch this point right here. First of all, this y equals 0 is going to be down here at y equals a negative 3. That's the horizontal asymptote now. And where did that point move to? So it moved back to 4, so that's negative 4, and then it was up at 1 and moved down 3. So this point right down here is negative 4, negative 2. And we have that same shape. Oh, isn't that nice? Now look at what happened here. The domain now is still all real numbers. That didn't change. We can still stick anything in for x that we wanted to. And then the range is now everything bigger than negative 3. And that's what we kind of hit there. Good. Now there are a couple of mistakes that are common with exponents and exponentials and with roots here. Some people will do something like this: square root of a squared plus b squared. And they'll be like, oh, I know that. You square root a squared and you get a, you square root b squared and you get b. And they think they can do this. Let's remind ourselves that long ago we learned something called the freshman's dream. If you have a plus b squared, that plus sign just ruined your life. You can't take that in there like that. That's horrible. So, what makes you think you can take a squared plus b squared and move this exponent in? You can't. That's bad news. You cannot do that. In fact, let's do it with some numbers and make sure you see this. 3 squared plus 4 squared, and square root it. Now, if you could do that, you take square root of 3, square root of 4, you get the number 7. Square root of what's 9 plus 16? That's 25. Square root of 25 is 5. Yeah, if you were to take that and do 3 plus 4, ooh, bad news. So yeah, this is a fraction version of the freshman's dream, which you don't want to be laughed at by generations of upperclassmen. Okay, good.